Okay, we should start. So what we're gonna do today is so for those of you, most of you who were at the class last week, we did a improvised live coding of reinforcement learning model in STAN. And now we're gonna take a step back and actually go through all the steps of how you build a model in STAN and discuss the different ways in which we can make choices about how to code it. And then we will move on to how do we integrate that in our R framework. I know some of you are using Python, but that's absolutely fine. You can just twist that part. And then we will start a whole block, which we should not finish today, but we'll carry on next week at the very least, on how do we think through a good Bayesian workflow for our models. That is, how do we ensure that the models that we are playing with, that we are implementing in our research or work, actually make sense? They can fit data that is generated by those underlying mechanisms, can reconstruct the right parameters, can identify mechanisms that are relevant, and so on and so forth. So we will do simulations for parameter recovery, prior posterior update checks, simulations for predictive checks, and simulation for prior sensitivity checks. So how do we ensure that the choices, what is the impact of the choices that we make? Which is going to be a constant refrain of the course, because we will always, as soon as you start doing complex analysis, as soon as you start building cognitive models, but even if you do any sort of machine learning or statistical modeling, you will need to make choices. And we make choices based on the best available information. We study, research how to make these choices, but there will always be choices. Other models would have been possible. And therefore, understanding the impact of the choices that we make on the model and on the results that we get is quite important. Good. So as we started seeing on Friday, we have a STAN script, which is separated in most cases from the R script. Actually, technically, you can write STAN in R, and in the course notes that I shared for ease of visualization, the STAN code is written within R. But it's a good practice to ask the STAN code separately also, because the R Studio or Visual Studio or whatever you use actually tends to have a syntax checker that helps you writing your STAN code. We've seen that there's three key blocks. One is the data, where we have to tell STAN which kind of data we're giving it. And it has lots of check inbuilt. That means we need to be very specific in saying which kind of data we're giving it. There's the parameters, which are those variables which we assume are involved in the data generating mechanism, but that cannot be observed and therefore need to be inferred. When we're talking about reinforcement learning, we cannot directly observe the inverse temperature. We cannot directly observe the learning rate, and this is where we define them. In a traditional general linear model, right, the intercept and the betas, the slope of the model, are things that we do not observe directly, but we need to infer from the data, and therefore they would be defined there. And then we have a separate block called model in which we tell Stan what the likelihood function is and what the priors are. The likelihood function is the function that connects the outcome to the parameters. How are the parameters together with the data generating the outcome? And the priors are, given that we need to infer some parameters, we always know something about these parameters. If nothing else, the scale in which these parameters are. And regions where there are more likely values, more reasonable values than others. And therefore, we specify these specific regions. This is often framed in terms of we can put pre-existing information that is previous studies there, which is a very valuable use. But in most cases, what happens is that we're just trying to make the problem simpler for Stan. We're trying to make the model to run in reasonable times. So we're mostly using the priors to rule out regions that make no sense. For instance, if we're looking, so the example, right? We're looking at the relationship between height and weight, right? It's not going to be, well, depending on the scale we're using, but if we're measuring height in meters and weight in kilos, right? We're not going to expect a beta coefficient of 1,000. It just doesn't work. It wouldn't make sense for our sampler to explore the region of parameter values. What if, I have to multiply my height by 1,000 to generate my weight? How well does it describe the distribution of weights in the class, right? It just doesn't make sense. If we're working on standardized effect sizes like Cohen's d, right? We know that the median of Cohen's d in social psychology is 0.2 something. So we will rule out, or at least tell the model that it's very unlikely that effects are going to be bigger than 1D, right? And that will actually restrain the space that the model has to explore in order to provide you a good solution. And it stands on what we know about these data, right? Just even in the scale of the outcome. And then we'll see that we can check how impactful these choices that we're making are. There's 3 additional blocks which we haven't seen on Friday. One is transform data. So sometimes the data provide certain kind of information, but they need to be changed a bit in order to be fit into the model. So let's say that the data that we have in the matching panels are my own previous choice, and your previous choice. But the reinforcement learning needs the feedback, right? Whether we want or not. So transform data would be a place where we can say, well, if the previous choice of the 2 was equal and I'm the matcher, right? Then the reward is 1. Otherwise, it's 0 or -1 according to how we're coding it. What happens, this is a small trick, it will become handy later. If we change things in transform data, these variables are not saved in the output. The transform parameters is a block where we can do the same thing, but about parameters. So we've seen on Friday that sometimes these parameters have boundaries. Let's say learning rate can only go between 0 and 1. And inverse temperature can only go from 0.0001 to infinite, but not negative. So we might want to create transform parameters. Let's say a logit learning rate, which allow us to do whatever we want with the learning rate, and only at the last minute invert the logit transformation so that it gets automatically squeezed into a 0-1 scale. This is generally useful, but it will become crucial when we will do multi-level models. Yes.
You said at the last minute, so does the transformation occur?
Well, that's when we specify that it should occur, right? Yeah. But the idea is that, yes, I'll just weave that into the example I was going to make, right? So I brought my own this time. So in a multi-level model, what we have, if you remember, we have a population level estimate, let's say alpha, right? The learning rate with a mean and the standard deviation. And from each of those, from that distribution, sorry, we say that the individual level distribution for participant 1, participant 2, participant 3 are sampled. And these distributions are defined as deviations from the population mean, the random effects. So this person might be, let's say we're in standard deviation, right? Minus 0.7 standard deviation compared to the population, their mean. And the P2 might be plus 0.3. And participant 3 might be, I don't know, plus 1. Right? If we have to specify that this parameter stays between 0 and 1, it becomes really tricky to specify a model that also ensures that when we sum up the deviations of the participants to the population mean, we are within 0 and 1. Does that make sense? Right? We would need to write very complex checks in the model that ensures that that happens. And that would mean throwing away a lot of the iterations of the models when that doesn't happen. And that would mess up the estimation space when we're, if you remember, moving as the queen mobile in the posterior parameter space. If there are places where we cannot go, right, that breaks a lot of the machinery of the sampler that's trying to use out the momentum, how fast we're going to explode better. But then it bumps against the wall and it loses that momentum. Right? So working on logout space is a way to say, well, here anything can happen. We don't really care. But as soon as it needs to be put into the equation of the reinforcement learning, we're saying that the alpha is the inverse logit of the logit alpha that we calculated here. And automatically the values go there, right? So we have that v at time t is equal to v at time t minus 1 plus alpha times the predicted error. And we say that what alpha is equal to the inverse logit. I think it's in Stan is just inverse logit. In R it would be inverse logit scaled of logit alpha, right? And logit alpha might be logit alpha I for the specific participant, right? Might be the population level logit alpha plus the subject level logit alpha deviation, right? So that we take the population level on logouts, we add the deviation that the participants has on that, we get a number, we put it here, and inverse logit transformation magically puts it back on the 0 to 1 scale. Does that make sense? This is what we would use the transform parameters to do, right? So we could technically do that also here, but we can keep it more clean to logically separating these different steps. In JAGs, which I think you've seen a bit last semester, right? Everything is just a big chunk. The Stan community, the good thing about the Stan community is that a lot of this discussion actually happened on forums, and I think at the beginning was Google group, you can actually go back and see a lot of these discussions. There was a lot of discussion about whether these would be too constraining or it would promote good coding practices. And that's what won, right? Just keeping things separated. The generated quantities is the last bit of Stan script, which is about creating. So as the model is sampling, right, it will figure out what alpha is, what the logit alpha is, blah, blah, blah. But when you want then to assess your model, you're going to need a bunch of useful variables. For instance, you might want to know, right, well, what was the prior for alpha for the learning rate? So that I can overlay it to the posterior and see how much the model has learned from the data. And you could generate it in R, but it's much more convenient to generate it here. Or you might have that the posterior estimate of your rate, right, in a random bias or in a Win-Staley shift model is in log odds. And that's kind of annoying to look at after, and you would need to transform it into inverse logit, therefore becoming probability 0 to 1. But you can actually do it here so that as it's has finished running the model, it can generate all the useful quantities in a fast way because it's running in C++ and save them all in the same place, all with the same format. The examples I've given you are the first thing that we're going to do, and they're going to be maybe not that pressing in the sense that a transformation is quite fast and easy to run in R, but we might also have a model with 8 parameters, right? Or even imagine a multi-level reinforcement learning model where we have priors for the population level parameters and priors for the individual deviation for the random effects. Right? And we want to know what would the model predict in terms of behavior for 10 new participants that we haven't seen before. And that would require quite some coding in R. And if the model is complex enough, it would also take a long time to run. So that's the kind of things we run here. We will also run the LU, that's the estimated out of sample error in a live one out setup, meaning what would be the estimated error of the model in predicting these specific data point in your data set if it had been trained on all the other data points except for this one. And that's something that takes a lot of effort. We want to let C++ deal with that, right? That's another thing that we write there. Good. But let's start. I'm going to go a bit fast because we've seen, yes?
Yeah, sorry, does the model output something automatically? You don't put anything in the...
Yes. So you're going to have the parameters.
What are the parameters?
Yes.
Okay. So if we, for example, want to save the distribution of the values to look at behavior.
The distribution of the values, which values?
The expected values.
Okay, yeah. So the predictions, yes.
Yeah, that we're doing the generated.
Yes. So for the people of the Zoom, when we create parameters, all of the posterior estimates of the parameters are saved, but the parameters are not the predicted behavior, right? So in reinforcement learning that we've been playing with last week, the parameters are learning rate and inverse temperature, but the expected behavior is the distribution of choices and rewards. And that's another thing that we would generate in the generated quantities. Good. Okay, so let's start from the very simplest model. That's the random bias agent and build up from there. Right. So what we have in the data, given it's a random bias agent that doesn't care about reward, doesn't care about what the other is doing, right? It's simply a sequence of choices. Right, left, right, 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 left. We're going to represent it here with a shaded square, which means that we can observe that variable. And it's a square because it's a discrete variable. I haven't been completely consistent in those. I need to update some of the plots, but I'm going to try to show you what's the standard in representing these models. Then we have, indeed, that should be circle. We have a latent parameter, a rate, that's traditionally called theta, which generates the choices through a binomial. In particular, given we're predicting them on a trial by trial base, a Bernoulli, that is a binomial that runs one trial at a time. And the sequence of right and left, of course, is also dependent on the number of trials, which is observed. We see how many trials there are. So in a sense, what we are saying is that this choice, which now is called right, is generated through a binomial that has theta parameter or rate and a trial equal 1, or is generated through a Bernoulli, which has a theta parameter, a rate. Those two things are completely equivalent. Stan is slightly faster at running the Bernoulli if you're running one trial at a time. Then what we need to do is we need to look at this model and say, well, what are the components of this model? We have the data, the sequence of left and right, the number of trials. We have a likelihood function that connects the outcome with a parameter. And we have a parameter. And we need to put a prior on the parameter. We had some discussions on these priors already last week. So I'm going to say that some people will argue for, oh, theta is a probability distribution. It goes from 0 to 1. We have no idea in principle, like these agents that we're playing against, they could be biased from 0, 0.1, et cetera, to 0.9 to 1, right? It could be somebody who just plays right. We have no idea. Let's just put a uniform distribution with these hard boundaries. It's a legitimate choice. In these contexts, it could also work, but it has two main problems. One is that, as I was telling you, anticipating you, the Hamiltonian Monte Carlo sampler, the system behind the Stan model that is trying to sample the parameter values in the region, doesn't like hard boundaries. Doesn't like to, you don't want the Queen Mobile to crash against a wall, right? You want the land that she's exploring to be continuous, so she can turn around and move and never be impeded by some arbitrary boundaries that you're putting there. So, an alternative is to actually implement a distribution that has the boundaries, like not hard-coded, but naturally emerging from the structure of the distribution. In particular, the beta distribution, which has two parameters. Well, there's different ways of parameterize that. In this case, the parameter is alpha and beta. So you have a beta parameter for a beta distribution, which I kid you not is an endless source of errors when you code, because which beta is which beta. And 1, is actually going to be very similar to the uniform distribution, but the sampler is going to have a much easier time. Or you could put a normal distribution, center at 0, standard deviation of 1, and then put an inf logit on that. This is what I like because it breaks very easily. And then I know what I did something wrong. The beta is very elegant. It works often even better for sampling, not always, but often. But I personally have a hard time with those parameters, the alpha and the beta, or sometimes it's the shape and the rate. All of them are good, just whatever fits your coding style, whatever fits your understanding of the problem. I know you've probably been doing some beta last semester, so I think it's a very good thing. It's just a question of coding style, right? Modeling style. Okay, this is how the Stan code looks when you generate a new Stan file. We put data, parameters, and model. And so what should we put in data? In the very specific example that we just discussed. Yes. The sequence of choices. Yes. Anything else? Yes. Right. The number of trials and the sequence of right and left. So we write data, curly bracket. We then say integer with a lower boundary of 1. That is called n, or however you want to call it, trial n, trials, whatever. And then we say array of size n of integers. And here I should update the example because I think the first time I wrote the code, it was about heads and tails. But since most of you speak Danish, let's say it's højre. Okay, so this is not super intuitive, but we have int. It's simply because Stan wants to know which type of data you're using. So it's an integer. Trials can be 1, 2, 3. They cannot be 1.5, 2.5. Lower, because if there's less than one trial, it just doesn't make sense. There's no data. And it's a nice sanity check because Stan will crash and tell us where the problem is if our data don't have enough trials. Semicolon, because Stan wants something to close each line. The array, well, you know what an array is. It's basically a matrix. In a lot of the examples that you see online in Stan, they're mostly going to use vectors and matrices. But the new coding style for Stan is arrays. And in a second, I'll be there. N tells it that it's a one-dimensional array, a vector, of length n. And we had to define n. If you don't define n, it doesn't know what to do with this. And then again, it's an integer because right or left, heads or tails, højre eller venstre, it's a binary choice, right? So it can only be 0 or 1 if we're using a Bernoulli, 1 or 2 if we're using a categorical. Right? There was a question there.
Yeah, why are you only, maybe it's stupid, but defining the lower bound, not the upper bound there?
This is an excellent point. So if we have an experimental design where there is an upper bound, let's say if they're still playing after 50 trials, throw them out, right? Then we would put that boundary in. In this specific setup, we haven't put a specific boundary, but you're right. So we put the structure in so that if by mistake, let's say when a participant starts playing against the computer crashes, but it saves the logs. Then the participant restarts and plays the full 50 trials. Suddenly in our pre-processing, there's 70 trials and we didn't notice, right? And you put the 50 trial as an upper limit, it gives us an error, we go back and check and we figure out the issue and then we decide what to do, right? Does that make sense? Good. All right. Now we define the parameters. What are the parameters in this very specific simple case? Well, it's the rate, right? Or theta. Can remember how I defined it here. It's a parameter which bound at 0 and 1. It doesn't make sense, a probability that's below 0 and above 1. So we specify that limit. We say it's a real because it's a real number. It can be 0.1. It has its name and a semicolon. Good. Now we have the model. What's the model? What's the likelihood function? Yes. Exactly. That generates age given. Yes. What else do we need to put in model? Yes. Good. So binomial given theta and n of 1 or Bernoulli. So in the model, and here I put some comments so it's easier to look at slides at a later stage. In this case, I'll do what Josh would do, right? So the prior for theta is a beta distribution with an alpha of 1 and a beta of 1. And now I'm going to use a slightly different way of writing it than I did Friday, and I'll explain why, which says target plus equal, meaning increment, keeps on adding at every iteration. Beta log probability density function that generates theta given 1 and 1. What is a log probability density function? What is a density function? A density function is simply the distribution of a continuous variable. A mass function, yes, mass function is the equivalent, but it's the distribution of a discrete function, right? So if you have, I don't know, a Bernoulli would have a mass, probability mass, while a normal would have a probability density, because the normal generates a continuous outcome. It describes a continuous variable. The Bernoulli, it can only generate 0 and 1s, right? So distribution and 0 and 1s. Stan is rigorous, so it forces you to specify D or M according to which kind of distribution you're talking about, so you know which kind of errors you're going to get. It doesn't have huge implications for the way we're using Stan, right? It just wants you to use the right terminology. Why log? Why do we ever want to work with log when we work with probabilities? All the model comparison things actually tend to work in log probability space. Yes. So it can, why shouldn't it be negative? Okay, so you're saying, okay, it's the equivalent of a link function, and it allows whatever we're sampling to also be negative. And then whenever we transform it back into probability, we exponentiate it and it becomes positive by default. Yeah. This is not the reason here, right? Because otherwise, since we're talking about probability, we would want it between 0 and 1, right? So log odds would probably be a better thing. So the reason here is that computers are discrete machines. They have a finite number of decimals, and they need to approximate when things are smaller than that. That means that when you work with probabilities that are close to 0, the approximation error can become quite big the more operations you make. And therefore, working on a log scale, transform these into a scale where actually being very close to 0 is being very, very negative, right? And you can go all the way to minus infinity. Yes?
So knowing that, why did we define theta as real rather than floating point? Can't actually explore the whole real number.
Because there is no real number space in computers. So it's as close as it gets.
We call it real number.
Yeah, because the conceptualization is that it's real. It's a real number, yes. Because here, so Stan is not a language like C, which does things as the computer actually does them, but it's a logical probabilistic language that is made to make us write our statistical assumptions as they are. And then when it gets turned into C++, it deals with all the nitty-gritty details of a discrete number space, right? Or approximated number space. Yes, but when we work on distributions in sampling, we always work on a log scale because of this issue. Because when there is a probability that can get very close to 1, the numeric approximation will potentially create lots of issues. I read somewhere, I have still to verify it, but I'm just going to tell you, so you know, it's also that, or some people argue that it's also because when you work in probability space, you need to multiply numbers. But when you work in log space, the log of a multiplication is an addition, and additions are much faster. I haven't tried it out. I don't know if that's true, but that's also one of the explanations that floats around. The other one is the most substantial one. Yes.
Just the pure more memory for like positive powers, like just have more memory for a million, and between a million and 1 and a million change. 1 part of a million.
Oh,
You know what I mean?
yeah.
Like,
So you're
this
saying,
explanation also implies that we can just.
well, so the point is that when you're working with probabilities, since we're working in an unnormalized posterior space, so we're not bringing it back so that it sums up to 1. If you multiply and multiply and multiply, it very quickly becomes very small, because multiplying a number by a number that's below 1 and above 0 makes it smaller. And it doesn't take many iterations for making it very, very, very small and reaching the number of decimals that the computer is using to approximate. Where it matters. Yeah, but so the point is that there is really no end in how many decimals there are, right? So even if you have a 0.1, 7, 2, 4, 5, 1, 2, 3, 4, 7, 5, right? It might have a very large number of decimals, potentially infinite. And the computer is going to cut it. And that means that it's going to make an approximation error. And these errors are usually less important when you're working with probabilities that are 0.1, 0.2. But if you're working with probabilities that are 0.0001, or multiplications of probabilities and not probabilities anymore, right? Just cutting at the 64th decimal place is gonna mess up your calculations, right? Simply because you're multiplying these decimal below 1 numbers, and it doesn't take that many multiplications to get to 64 decimals, right? And then you need to normalize it back, but since you cut all the useful information after that decimal threshold, you're not going to get out what you needed to get out. Does that make sense? Why, when you work with millions, right, you can go up, but the decimals are not going to matter, right? Because you're working in a number space where decimals, who cares? Does that make sense? Are we going too technical? None of these is super important when you're fitting models, right? But I just want you to have, like, what is this stuff, right? Why are we writing this shit? Because up to a couple of years ago, we would have written theta tilde beta 1, 1. Doesn't that make more sense? I love it. But they decided that we need to understand better what's going on. So this is the best way of writing it. Because what this is saying is, first of all, we are working on a log probability space. We are working on a density function. And remember, when you're sampling a Bayesian model using Stan, you never generate the full prior distribution, right? what you're doing is you're saying, hey, I'm the Queen Mobile, right? I'm testing whether a rate of 0.6 is good. And how do I test that? Where I see how well would it generate the data, right? Out of 10,000 simulations, how many times would I generate the data that I'm seeing? The sequence of left and rights that I see. But also, given the prior, what is the, now I don't want to get it wrong, but what is the probability of 0.6 as a rate being sampled from this distribution? And then I put those two together, and since we're in log space, I can just sum, make it neat. And that will tell me my log posterior likelihood in this space. I'm never going to just sample from the beta distribution to generate the prior distribution. I'm only going to check, given these rates that my sampler is generating, what's the probability within this distribution? And so these kind of notation seems to imply that we generate the full distribution. This one says, no, we just generate it on a sample by sample base. And then we add it to the ongoing calculations of the log posterior probability, log posterior likelihood, sorry, which is the target of our work. So we want to know, given this distribution of posterior parameter values in the model, how good our model is at explaining the data. I know this is technical, right? We will go through these things again and again. I just want you now to have the full perspective on what the heck we're writing. So basically, this is a prior. We need to specify what's the distribution, what are the parameter values in that prior. Stan makes us aware that we're working log probability space and that it's density if the variable is continuous, beta, or mass if it's discrete. And then we specify the likelihood function, which is specified in the same way, right? Because they're both going to contribute to the log posterior likelihood. And it says that there is a Bernoulli distribution with a rate of theta. Bernoulli underscore log posterior mass function, because it generates 0 and 1s, where H is generated from the parameter theta. I know this is not the most fun part of programming, but we can understand what goes on, so that actually enables you to program more fun stuff. Good. Any questions on this? Yes.
So the target is that the generated value from the distribution.
It's the target. No, the target is, given that we're building a sampler. So imagine the Queen Mobile that goes around Denmark, trying to find the regions in which there's most people to breed. And the target is, given where the Queen Mobile is now, how densely populated is that area? That's the target, because once we have that, then we can say, well, let's look around. What's the gradient of population density around me? And that will sort of sway the car in the direction in which the gradient descends faster, right?
So I'm just trying to understand, after the first iteration, what will the target, like the value that's called target, what value would that take?
Okay, so it's going to be in a log space, so it's going to be a minus infinite to plus infinite space, right? So let's say that, so what it's going to do is just calculate, let's say we have a theta of 0.6, right? And according to the prior, right, maybe it's centered at 0.5, right? Well, no, it's basically uniform. So it's going to say again, let's assume that only 0.1, 0.2, 0.3 are possible, right? Not 2 decimals, but 3 decimals. So that would be 11th, an 11th of 1. So 1 divided 11, that's 0.08, something like that. 9. Damn it. My mom would be so disappointed. Yes, so that's 0.08. Can you do a log of that?
Hold on.
I can do
Minus
log.
1.04.
Yeah, so that would be minus 1.04. Great. Then let's imagine that our sequence of, how would we calculate it? So we would have a sequence of left and right where whatever, I'm just gonna make it up. I'm not gonna generate the sequence and then calculate the thing, because this, I haven't prepared it, and it's nice if I can sit and calculate and then make it in the slides. But let's say that it would be a 0.04. Can you do the log to 0.04?
Minus 1.39.
Yes. Minus 1.39. So this is what these two are generating, right? At a given sample. So what we do is we just sum them, because they are combined. They give us the posterior probability of this value of rate, right? So the prior times the likelihood normalized, which we don't do because we do samplers, gives us the probability of these specific value of the parameter given the data, right? Bayes theorem. The posterior is the probability of a parameter value given the data is equal to the prior times the likelihood. That is this thing and the probability of the data given the parameter value. Yes?
Can you just repeat what it was in fewer words?
Yes. Yes. What your classmate is asking me is what happens here at one sampling, right? And what I'm saying is here we calculate the prior probability of a given value of rate where we randomly happen to start. And here it's giving me the likelihood of that value of rate given the data. The posterior in probability space is this multiplied by this. In log space, because multiplication in log space becomes addition, is this plus this. So the log posterior probability of a rate of 0.6, we said, given the data and the prior, is at the first iteration, right? I can do this. 3, 4, 2 minus 2.43. What does minus 2.43 mean? What's that scale? The point is, who cares, right? Because we're always working in terms of relative likelihood, right? It's like, what do AIC mean? Those values per se will change according to the number of the data points that you have, a lot of the structures in your model, et cetera, et cetera. It's only when we go and compare things. And indeed, what the model is going to do is looking around and saying, if I shift a bit, well, this is a two-dimensional space, so it's easy. If I go to point, we said also we simplify, it's only one decimal space. We have a very stupid computer, right? It looks, well, if I go to 0.7, what's the score? If I go to 0.5, what's the score, right? And that, since it just started, it doesn't have a momentum, right? And so it's just going to go towards the one. It's going to slide down the hill, right? Towards the one that has, so if this is a log probability, the one that is a higher one. So if in one case it's going to be minus 2.6 and in the other is going to be minus 2, it's going to slide towards the minus 2. Right? And it's going to gain some momentum because there is a slope here, right? A 0.43 of difference, which means that then it's going to look here around. And in one dimension is stupid, right? Because it can only go to whatever. If it went towards 0.7, towards 0.8. But let's imagine we were in a two-dimensional space, right? It looks around, and then maybe here it would be keeping on going in that direction. It would be minus 1.8, and keeping going to this direction, it would be minus 1.7. So if it had no momentum, it would go towards the minus 1.7, right? But it has momentum going this direction. So it will be swayed this direction, right? There is still a slope, it's not going up. But instead of going this direction, it keeps the momentum. And that's what Hamiltonian Monte Carlo does that a lot of other samplers don't. It explores this space with like so much enthusiasm that it keeps going even if it's uphill, right? Yes.
So is the target then, would that then be taking the minus 2.43 and then in the next round you add minus 2 to that? And then yeah.
Okay, yes, this is a good point. Now, the target plus equal in this specific thing is saying at a given sample,
Yes.
at a given iteration, it's summing those two up.
Okay.
Then according to what we're trying to calculate, if we want a total number, like one number that tells us the log posterior likelihood of the model, but then we just want to pointwise compare to a different model, for instance, then we just can keep on summing up.
Yeah.
And that would give us the number we want. Because it would add more often the numbers of the places that are better at describing the data. If we want to diagnose the model, right, and see where it's exploring and how it's going, how the momentum works, we might want to save all these separate ones. But yes, for the calculations of that we'll see of leave one out, estimated error, and so on and so forth, it will just keep on summing. Does that make sense? Yes.
So keep on summing that what?
So if we want a measure of the model fit, yes. But for the sampler, it doesn't matter because the only thing that it needs to know is its momentum and the slope around itself. Right. So it only needs a memory of one in a sense. That's why it's a Markov process. It's a process that loses its memory beyond one step or two, right?
So in the next iteration, we draw a new theta. And then compare that to the direction we're going in.
So technically, and then we'll take a break. Here is the, let's say it's a two-dimensional space. We start somewhere random. What we do is we approximate, because we're using a computer, it's a discrete machine. So we say, let's go in this direction. We sample the gradient around this. We calculate where it should go. We sample here, and then let's say there's 3 live frogs, they're called. And then here, we have a sample. Then we repeat the same process. And here we have another sample. So we keep starting from the point where we are, And if you want that level of independence, what would happen if we start at a different place? That's why we run more than one chain, and we'll get there. Because then we'll restart a completely different place. Good. Let's take a break. 10 minutes break. So basically, the intuition here is that at any step of the sampler, right, we have a given value of theta, which is determined by our exploration of the parameter space. And we calculate its log posterior probability or likelihood by summing how likely it is given the prior and how likely it is given the data.
Can you repeat the last part?
Yes.
So we calculated something.
Yes. So basically, given the way that we're exploring the parameter space with our Hamiltonian Monte Carlo, at any given iteration, at any given point in time, we will have a value of theta.
Yeah.
In order to calculate its current log posterior likelihood, what we do is we sum up how likely it is given the prior and how likely it is given the data.
Yeah.
In this way, the prior is constraining our exploration of the space at every step of the process.
Oh.
I was telling to some of your colleagues that not about the specifics of the sampling, but about the general operation that we're doing, what really helped me understand how samplers are magic is if you have a square that has a side of 1 meter and you inscribe a circle inside and you want to know how big the area of the circle is, well, you can Google it, and there's lots of interesting history of the problem with people basically killing each other by letter about how do you create the math to do that. And actually, I'm not sure whether it's currently solved or not as a problem analytically. Well, let's say that you just create this 1 meter by 1 meter square with walls around, and you draw the circle, and then you take 1,000 coins and you throw them inside. You can simply count how many fell within the circle. Let's say it's 87%. That will tell you that 87% of the area of the square, which is 1 square meter, meaning 0.87 square meters, is the area of the circle. And you didn't need to do any math, right? Just count it. That's basically what these numeric Bayesian statistics is helping us do. Because Bayes' theorem says that the posterior probability, the probability of the parameter values given the data, is equal to the prior probability, right? The probability of the parameter value, no matter what, times the likelihood. Right? The probability of the data given the parameter value, and that's the easy part. But as you multiply two probabilities, you're out of probability space, which means that you need to normalize all these values so that the distribution sums up to 1. And you do that by dividing prior times likelihood divided the probability of the data no matter what, which is the tricky part to calculate, which requires complex integrals. What we do with the sampler is we don't want to normalize. We don't want to spend our days writing integrals, which are fun, at least from what I remember from high school, right? But they really come in the way of fitting them up. So people would spend chunks of their careers developing the specific solution to a specific model. We don't want that. We want just to run on any kind of model. So what we do is we do this magic, right? We explore the posterior space. We're going to have these meaningless values, right? Because they're not normalized. But if we save the parameter values that we explore at each point, we will visit the different regions of space with a frequency that's proportional to the probability density. That's magic. Right? And that means that we can simply count how many times out of all of the iterations that we have, we visited that specific region of space, and that will give us a measure of its probability. I see you have a question blossoming there.
No, it's just the target. So the target could have been called log posterior phase. Or what?
We have here the log posterior, right? Yeah. So target, yeah. But basically what target is saying is this thing is not just the effect. So target is not just the effect of the beta log probability density function, but it's a function of all the probability and mass functions that we have in this model at the same time. So that when we have more parameters, we can have more priors. And when we have models that might have more than one likelihood, which happens, we might have more likelihoods. Okay, a statistician would tell a combination of likelihood is still one likelihood function, but yeah, we'll see that later. Good. I hope you're not too hopelessly confused, but you're confused in the way that says, ooh, there's something that I need to understand that I didn't understand before. Good. All together, right? This is the data block, int lower 1n, array n, int h. We define the parameter, we define the prior, we define the likelihood function. We've seen it all together. I want to show this because often what happens is that you write these in RStudio. I don't know how it works in Visual Studio, and it will tell you that the array part is wrong. And that's simply because RStudio relies on RStan to do syntax checks. And RStan is fighting with CRAN basically to get their latest versions approved. So if you want the syntax checker to accept array and all the new notation, you just install it from the mcstan repository. But only if you get errors. Good. So, weren't we talking about log odds on Friday? Right. Why again were we talking about log odds? Well, I guess I've taken it up a bit on the whiteboard here, right? How do we implement it with a log odds? Well, it's relatively easy, right? What we do is, well, since people realize that log odds really save your life in a lot of cases while confusing you at the same time, there is a nice Bernoulli logit that takes theta in the format of log odds. So you don't even need to worry about the inverse logit stuff within the model. And then instead of having a beta or a uniform distribution here, you can just have a normal prior for the theta with a mean of 0 and a standard deviation of 1. Right, that's the only thing that I changed. Here I have a prior that's a normal distribution instead of a beta. And here I told Bernoulli, the Bernoulli log probability mass function, that the rate is going to be on a log odds scale. And then, given that nobody understands log odds, no matter what they tell you. If they say they do, they lie. In the generated quantities, what we can do is we can say, oh, there is a new quantity, a new variable that we are interested in, which is a real number with a lower boundary of 0 and upper boundary of 1, which we call theta p, or theta posterior, theta probability, I think, which is given by the inverse logit of theta. So that in the output of the model, we're also going to have a nice theta p parameter, which we can read and understand. Does that make sense? Okay. I have a message for you from previous students, which is, remember, you do the inverse logic only at the very, very end. So let's say that you have a model that has alpha plus beta times the previous rate of write, right? A memory model of some kind. You don't do the inverse logit on the alpha. You don't do the inverse logit on the beta, right? It's only when you put all of them together into a rate that determines the heads or the choices that you do the inverse logit. You work in log odds till the very, 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 very end. Because as soon as you start doing inverse logit before the very, 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 very end, you're going to make mistakes. Good. So it's a nice model you have there. It'd be a shame if somebody were to fit it to data. Right? That's where you finally made it, like it passes the syntax check, and then some data arrives, and it's terrible. Okay, how do we prepare the data to fit that model? Here is the data chunk in the stand code, right? Nothing new. So we need to pass it a number and a vector. So if we say that D1 is the data we generated from one random bias agent with a rate of 0.8, right? The data for stand is a list where n is the number of trials, if you remember. And in the simulation, we had 120. We could just say n row of D1. That would also work. That probably would be more elegant. And the age variable is the choice column. So it's a list. It's not a data frame as we used to. Why? Well, lists are more flexible and Parsevaldians than data frames. Data frames are really ergonomic, right? They're really neat because they say for these data point, we have all the data, all the metadata in one row. But that means that you're going to repeat the same information many, many times, right? So if you have the age of your participant and you think that's an important predictor, because we know that with age, I don't know, learning rate decreases or whatever, something. Right? We need to repeat age in every row of the data frame. If there's 120 trials, every age gets repeated 120 times. Does that make sense? This is more flexible and more parsimonious. And when you start doing very complex models, you start worrying about saving space and that sort of things. Okay, then you specify where the model is. You give it a file path, and whoops, that's a really bad practice, right? You don't want to write the complete path, but I couldn't be bothered to remake the screenshot. What you do is you use projects, right? And then we create a model file that has the common stand model with the file, which is the path of the stand file. And here I wrote something which is also at this stage a bad practice, but Stan has now implemented a way of parallelizing the sampling, meaning that as the sampler is looking around to see what the gradient is in that region of parameter values, that is, where's the biggest slope, basically, right? That's very computationally demanding, and they figure out a way to split it across cores. If you change a bit the way that you write Stan, and you specify that when you compile your Stan file, then it can actually parallelize across many, many cores. But I haven't managed to make that parallelization yet part of the course. So that's just a placeholder. You know it's possible. And if you Google reduce_sum, there's plenty of discussion on how to do these things, but they work differently for different models. So I haven't figured out a good pedagogical way of going through that. Okay. Then what we do is we basically say that these object, the model that we compiled there, should be sampled. And it should be sampled given this data set. Then I put a seed just because it's more reproducible, but you don't need to. Then we need to specify, as we're running our Queen mobile in the posterior parameter space, how many Queen mobiles should there be, right? And here we say 2, because we can start seeing whether the 2, as they explore the space, they go to the same places with the same frequency. Because if they do so, then, of course, we might still have been unlucky, but we're a bit more secure, confident that this is really the structure of the space. Then parallel chains says, should these chains run one after the other? That is, we first do our first exploration, and when it's done, we restart. Or should they be run on 2 separate CPUs? And here I say, please run it on 2 separate CPUs, so I don't need to wait twice as long. Threads per chain is the placeholder for that, right? How many times should these be split? So each chain can be split across multiple cores. Now I wrote 2, but that actually should be deleted because it's not making a difference now. Then we have a bunch of things here that we haven't properly discussed yet. Iteration warm up, iteration sampling, refresh, max 3 depth, and adapt delta. What are these? Well, if you remember, what we are doing is we are exploring the posterior space. And given we're starting at random, we, first of all, might be starting very far away from where the real posterior density is. This is what in JAGs would be called the burn-in. Like you want to sort of get it to run a bit before you actually start keeping those values, because at the beginning you might be starting very far away. But the true reason in Stan for having the ITER warm-up is because the algorithm that's exploring the posterior space is a smart algorithm that fine-tunes its own parameters to better explore your posterior space according to the structures of your posterior space. What does it mean? It means that, sorry, people of the Zoom, I'm going to do another silly drawing, but I'm going to describe it. Actually, no, I'm actually going to go on the internet and show it to you if I put it here. Do I have it? No, I don't have it. Let me just find it. Gibbs. Gibbs. Yes. Okay, so let's take the Hamiltonian Monte Carlo, and then let's stop it because we cannot really. Where is that? Stop. No, where do I stop it? Oh, autoplay. Yes. Then we reset. And so basically, what you see on the screen is the posterior space. It's a two-dimensional posterior space, two parameters that we need to explore. The darker the shading, the higher the posterior probability. Right, so basically what we want to find is this shape. And that's really the combination of, you can see it here, two simpler distributions, the x and the y-axis. How do we explore this? Well, we start somewhere. That's where we started. And then, okay, what is this doing? So it's going at random in one direction. Or sorry, it's sampling the gradient. Here, there's not really much difference, but there is a bit of gradient. It goes here, then it goes the third step, then it moves around, it finds some density in the blue, and you can see that the steps are getting longer, right? It's getting faster. The Queen Mobile is going faster here. And then it's going uphill, right? It's less and less likely, so it comes back, right? And then it ends up here. And you can see that it's doing a lot of small steps. What are these steps? Well, the point is, again, we are simulating a continuum system. The computer is a discrete machine. So if we want to observe the trajectory of a particle or a simulated particle, which is moving according to the gradient, we need to now sample is a bad word, but we need to check a few times, right? Because the trajectory can only be shaped if we move around for a while, right? So these are the leapfrog steps. The second thing that is important is how big these steps are, right? So if this was the Queen Mobile, right, we could sample or we could check it once a second, right? And the distance covered by through 1 second depends on the velocity, of course, right? On how fast we're going. And that's where you can see they're different. So the algorithm needs to learn how many times it should check the trajectory before measuring the sample, and how big the steps or how often it should, right? So if it's 37 leapfrog steps, right, should they be every 1 second or every 2 seconds, every hour? And of course, these parameters, different values of these parameters will explore better different structures in the space. So if you have very narrow distributions, you want small steps, right? You want to check it very often. If you have very sparse distribution, maybe even multimodal, you don't want to check too often, otherwise it's just gonna fall back, right? The burning or warm-up steps are simply the steps in which the sampler is fine-tuning those parameters. How does it fine-tune these parameters? According to a learning mechanism, which we can set up here. The default is 0.8, if I don't make a mistake. I am the kind of person who really hates to have to rerun a model. So I put it maximum learning, which means that at the beginning, it takes actually quite a long time to go through the warm-up, where I can read papers. That's the time I can, or rate your assignments. But then it's really tends to be much more optimized to difficult posterior spaces. Yes.
So at that delta only affects the warm-up session.
Exactly. So Well, so it has something to do with the sampling afterwards in the sense that changing the adapt delta will give you different fine tuning
Oh, yeah.
of the parameters. Yeah. The max tree depth is a bit more complex, but if you remember what we were seeing here, basically the model has almost come back in the same place. And so what the algorithm can do is to sort of look into the future and say, if I'm gonna do a U-turn and just keep exploring the same area, well, maybe I shouldn't follow this path. And the further you have, the bigger you have your tree depth, the more sure you are that it's not gonna do that. But the slower the algorithm is running. Iter sampling is once the algorithm is fine-tuned, how many times it should run. Right? And here it's sampling 2,000 samples per chain. The refresh is simply how often it's going to tell you that it has run those iterations, right? If you put 500, it's going to tell you when it's done 500, 1,000, 1,500, 2,000, 2,500, 3,000. If the model is very slow, you might want to put it much lower so you actually see whether it's sampling at all. This. Okay. Does this make sense? Good. We run it with the beta prior that we've seen before. We run it with the logit normal prior. We say samples, if you remember, sample is what we saved, and it's an object. And then we say, give us the summary. So use the, now I forget the right term, but the function, the method summary on the object samples. And it gives us an overview of the posterior variables. We have theta, which you know, right? It's 0.755. It gives us the median, the standard deviation, the mean absolute deviation, maximum absolute deviation. I can't remember. It's like a measure of variance, which is not swayed as much by outliers. The 5th percentile, 95th percentile, and then some stuff that you don't know yet, right? Which we're gonna cover, but let's do one thing at a time. And then it gives you a log probability. What is this? Is the output of target at every step. So it saves, you have it there. So you can see if there are certain, oh, actually, and it does that. Yeah, it does that for every sample. Yes, you can see where there are some samples where it was being led astray and stuff like that. If we run our second model, it looks pretty much like that, except the theta is 1.11 because it was running on log odds. And 1.11, who knows what that is, right? But we generated the inverse logit in the generated quantities, right, which is 0.751, which is interpreted. So you can see that the parameters that are in the model and the generated quantities are outputted in exactly the same way. That's where it's very convenient to generate stuff. Good. We're gonna deal with this more in depth next week, but I just want to show, so here is if we have a beta with 1,1 parameterization for parameter values. The prior distribution is the red, and the posterior distribution is the blue one that you see here. What we are seeing here is that there is lots of uncertainty to start with, but the model is learning a lot. Right? It's becoming much more confident after seeing the data. We also see that the estimate at 0.75 is not exactly what the data was telling us. Because we know since we generated the data that the true bias was 0.8. You might have missed it. It was in a slide. I didn't emphasize it a lot. Now we can see the same plot for the other theta in the second model. You can see the normal distribution of the prior, which is centered at 0. It has a standard deviation of 1, so lots of the probability density is between -2 and 2, right? And then it decays. It's a normal distribution. And we see again that the posterior has become much more confident, and it's at 1.11, whatever the heck that means, right? But of course, right, it's kind of odd to compare these two plots because the one on the left is in probability space, the one on the right is in log odds space. So we can invert logit in the generated quantities, also the prior, and then what we see is the distribution of the priors is a bit more pointy than the one in the beta distribution. So it discounts a bit extreme values of rate. But the general picture doesn't change. Right? Yes.
Same data, it's just different. So it's probability space and log odds space.
So the first panel on the left is a model that has a prior with a beta distribution. So it's a different model. The second and the third panel are from the same model, but the second is when we look at it in log odds space, and the third is when we look at it in probability space. And I'm showing this because now it's kind of trivial, but we will see with more complex models that it becomes very important to be very aware of which scale you're looking at things. I should have put it here. I haven't, but let's say that we wanted to be, we looked at the third panel and said, this is really not comparable to the beta one, and we really want to be completely uncertain about where the posterior probability or the prior probability of the rate values is. So we give it a mean of 0 and a standard deviation of 5. Right, it's very flat in normal space. What would happen when we turn it from log odds to probability space? So what would happen, and for the people of the Zoom, sorry, I'm drawing it, but is that basically everything that is below -3 is 0. There's a lot of stuff below -3 in a normal distribution with a standard deviation of 5 and a mean of 0. Which means that in probability space, you would have a new U-shaped probability distribution. Which means that you thought you were telling the model, we know shit about this. But actually what you're telling the model is we're really, really sure that rate is either 0 or 1. And that's where link functions, these transformations are really magic, but you always need to visualize stuff to really understand what your model, what you're telling your model to do. Does that make sense? Good. I don't think, let's see how this would work. Okay, yeah, I can actually get this. So let's imagine though that theta is not just a parameter we need to estimate, but it's actually a parameter which is determined by a more complex model, right? So it could be the Winst-Taylor shift, it could be a memory model, it could be the reinforcement learning model, right? So we want to understand, how do we put stuff into theta? How do we generate theta from other stuff? So most of these is the same, right? Rate, right, so the choices, trials, the sequence. But what we are saying is that theta instead should be generated according to a linear model in log odds space, right? with an alpha, that's going to be a bias. Is the participant more biased towards right because they're right-handed, for instance? Times second term, which keeps track of how often the opponent has played right, and weights it according to a beta parameter, meaning it can follow it deterministically, or it might only follow it with a probability, right? So the way that we change this is we add two parameters, alpha and beta, that are determining rate. And we have something that we conceptualize as observable, right? The memory state, in the sense that we can count how many times out of the trials the opponent has played right? We can just feed it to the model for simplicity. And then we would have that, we need to put priors. We can put a prior on alpha. That's very broad. We have no idea whether this participant has a right or left bias. Normal distribution with a mean of 0, standard deviation of 1. And then the beta is a bit more constrained, right? Because we want the model to really show that the participant is using memory. The normal distribution with a mean of 0 and a standard deviation of 0.3. Again, why 0.3? Well, I have some experience in this, but we'll get into where you check the input of putting 0.3 or 0.4 or 0.5 and then make choices accordingly. And then the theta is the inverse logit of alpha plus beta times memory. Right? We take that equation that was up there before, and we just, at the end, after we summed up and multiplied everything, we do the inverse logit and turn it into a probability. One thing, though, to consider is what's the scale here? So if memory is inside an inverse logit transformation, everything that inside an inverse logit transformation should be on log-out scale. This makes a lot of sense because what we want is that if memory tells us to go right, it should be a positive number. If memory tells us to go left, it should be a negative number. By putting memory on a log-out scale, so the mean of the previous trials, if we code right as 1 and left as 0, is in probability space. We transform it into a log-out space, and automatically we get for free that it's pushing us one direction if there is more evidence for right, and it's pushing us in the other direction if there's more evidence for left. It's positive in the first case, it's negative in the other case. And here is the code. Right, we have integer that tells us the number of trials. We have a vector of integers that tells us the choices. We have a vector of integers that tells us the others' choices. We have two parameters, the alpha and the beta, and I'm calling the alpha bias because it's more intuitive. And then let's forget that for a second. We put two priors on the two parameters, one prior each. And we have the Bernoulli logit LPMF, where the choice at a given trial, and I'll explain you why we're doing it trial by trial, is given by the linear model that we were seeing before. Right? So alpha or bias plus beta times memory in that trial. Now, what I wanted to show you, and again, I sometimes get overambitious and say, oh, this year I can also teach this. So apologies for running a bit faster this time on this part, is that if we only take the actual observable, right, what I chose and what Mina chose, we can create an internal vector that creates memory on a trial by trial basis, creates and updates memory, which means that if you have a fancy function for your memory that you want to use, exponential decay or whatever, it gets easier to do it here. And basically what it's doing is in the transform parameter, we have a vector for memory that runs through the trials one by one. If the trial is number 1, then memory should be put at 0.5. There is no memory, no evidence for the one or the other. If the trial is above 1 and less than n, and I can't remember why I had to put, oh, because the last one is a bit tricky, yeah. Then the memory for the next trial is given by the current memory plus the predictive error divided how many trials we are in. This is a Kalman filter, which basically allows you to run ongoing mean of a sequence without having to remember all the previous steps. You just remember the mean, the current mean, and how many trials you went through. And I can explain this better next week. And then I had to put a trick, because if it went to 0, log odds of 0 is minus infinity. If it went to 1, log odds of 1 is plus infinity, which crashed the algorithm. And that means that just by seeing the choices which are actually observable in the data, the model is updating its memory, which I think is super neat. And I'm letting you go. Tomorrow, I think it's tomorrow, we'll start assignment 3.